time for a new direction. We move from our old problem of how do we make new groups from old ones to the new question, when are two groups equal? So now that we have enough theory and enough examples, it's worth asking when we're given two groups, how do we know that these two groups aren't the same, perhaps with different labels? To motivative definitions, we take a step back to set theory. Now, in set theory, okay, we're talking about sets. There's no real structure for sets. So the idea is all we can do with sets is count points. If we had two finite sets, to tell whether they were equal or not, we would just count, and if they had the same number, as sets go, they would be equal. Okay, we would say they have the same cardinality. If we had infinite sets, the way we tell that they're equal is by constructing a bijection between the sets. And then that's our definition for cardinality in that case. So, what's a bijection doing? Well, think of it this way. We lay out all the points. We're going to take away all the labels for x. Then we're going to replace with labels for y. And every point is going to get exactly one label. So that's what we're doing with a bijection. We're not affecting, okay, the underlying thing. We're just changing the labels of all of its points. Now, if we move to groups, well, groups are sets. So to have two groups equal, we would want them to be equal as sets, meaning that we can construct a bijection between the sets. But groups also have a multiplication, so on top of that, we're going to want that these bijections preserve the multiplication. So if we multiply two elements, apply our bijection, should be the same as if we just apply the bijection to both our elements and then multiply on the other side. So that's going to be our definition. We want two groups to be the same if on the set level they're equal, so we have a bijection, and then we're going to want multiplication to be undisturbed by the relabeling of the points, by the bijection. Now, we focus on the second part for this talk. So, if we have a map from one group to another that preserves a multiplication, we call that a homomorphism. So, we have pi going from G to H, homomorphism, if pi of xy is equal to pi of x times pi of y for all x and y in G. So here, we're multiplying in G, applying pi. Here, we're going to apply pi and then multiply in H, and then they're equal. Now, if we have a homomorphism without the bijective property, how should we interpret that? So, if we fix our group H, we let our group G vary, and we let the homomorphisms from those G's into H vary. What we're doing is exploring the multiplicative structure of H. So these G's are all going to have different types of multiplicative structures, and with the different ways we can map in, we could see if we could reveal information about H. Now let's look at some examples. So if we have any group, we have the trivial homomorphism, which just says send every element to the identity element in H. Now, if we take x times y and apply pi, okay, whatever goes in comes out the identity. So we have the identity here for H. If we put in x and y into pi and then multiply, we get the identities for H, we multiply, and then out comes the identity for H. So these are equal, so homomorphism. At the other extreme, we could take homomorphism from G back to itself. So here H is equal to G. We're just going to send each element x to itself. So in this case, whatever goes in comes out the same way. So if xy goes in, we get xy out. If we put in x, y into pi and then multiply, out comes x times y. So these are equal. So again, homomorphism. For things a little bit more concrete, I could take our G and our H equal to the integers under addition. We'll take the homomorphism, send each integer to 2 times the integer. If we apply pi to the sum L plus K, we get 2L plus K. If we do it separate and add, okay, here we're using addition for multiplication, we're going to have 2L plus 2K, and these are equal. So homomorphism. For another, we'll let G be equal to the reals under addition. Our H is going to be the positive real numbers under multiplication. The way we map, we're going to send each element in the reals under addition to e to the x. If we take the sum, so that's going to be the multiplication in G, addition, we apply our homomorphism, we get e to the x plus y. If we apply pi separately, we get e to the x, e to the y, and then we multiply in our h, which is genuine multiplication. So these are equal, so homomorphism. Final example, let's let our group be equal to S3, the symmetries of an equilateral triangle. So we label it 1, 2, 3. And our h is going to be plus minus 1 under multiplication of numbers. So what we have here is going to be called the sign homomorphism. Sine of x is going to be equal to 1 if x carries the top of the equilateral triangle back to itself. We'll let sine of x be equal to minus 1 if it switches the top and the bottom. So we've looked at this before, okay, type of symmetries that keep the top going to the top or switching the top with the bottom. So we have x equal to the identity in the rotations in the first case and the reflections in our second case. To see the homomorphism property, we'll check on a few examples. So we want to show that sine of xy equals sine of x times sine of y. If we use 1, 2, 3, and 1, 2, product is 1, 3, and that goes to minus 1. If we work it out separately, we have a 1 and a minus 1, so that goes to minus 1, and it checks out. If we use 1, 2, and 2, 3, the product is 1, 2, 3, we get a 1. If we work it out separately, we get a minus 1 and a minus 1, which gives us a 1. Now, for a large class of examples, let's consider G to be any group. N will be a normal subgroup of G. We'll consider G modulo N, the quotient group. The space here is just the set of cosets by N. For our homomorphism, okay, the quotient homomorphism, we're going to have Q sending G to G mod N. It's going to be a surjective map. And we send Q of the element X in G to its coset, so Xn. Now the homomorphism property is just the fact that we have a multiplication on cosets when we have a normal subgroup. So this will look familiar. If we apply pi to xy, we just get xyn by definition. If we work it out separately, we have xn, yn. N is normal, so we can replace ny with yn. And then n times n is equal to n, so we get xyn. And these are equal, so we have a homomorphism. For an example, we'll let our g be equal to the integers. Our n is going to be the integral multiples of n. And so here our quotient map is just carrying the integers to z modulo n. So k is going to go to k plus nz. Now, a few facts that are useful when we're working with homomorphisms. So we'll have pi homomorphism from G to H. Pi is going to carry the identity element for G to the identity element for H. And we're to have the inverse of pi of x is equal to pi of x inverse. So the inverse sign factors through our homomorphism. Now for the first one, we'll take the product, EG times EG, apply pi. EG times EG is just EG, so we have pi of EG. But we could split it up and write it as pi of EG times pi of EG. Now, I can cancel pi of EG on each side. Note, once we've applied pi, we're working in H. So what will be left over here is going to be the identity element for H. So pi of EG is EH as promised. For the second one, okay, we're going to use our trick, which is if I want to know the inverse of pi of x, I look for some y in the group. such that if pi of x times y is the identity, then that's going to be our inverse. Okay, the inverse is going to be unique, so it has to be y. So our guess is pi of x inverse, so I'll multiply pi of x times pi of x inverse. By the homomorphism property, we can move things to the inside. So I have pi of x, x inverse, which is e of g, and then we apply pi. By 1, this is just going to be e of h. So we found our candidate for the inverse. So the inverse of pi of x is pi of x inverse, again as promised. Here's an interesting connection between normal subgroups and homomorphisms. If I have a normal subgroup in G, we can associate to that a homomorphism Q sub n, quotient homomorphism using n. We're going to see in the other direction, if we have a homomorphism pi, we'll be able to attach a normal subgroup to this homomorphism. So definition, we have pi, a homomorphism from G to H. The kernel of pi is going to be the set of all x in G, such that pi of x is equal to the identity in H. So the analog here from linear algebra, if you've had it, is the kernel of a linear transformation. So that would be the set of all vectors that are sent as 0. Now, proposition, the kernel of pi is a normal subgroup in G. So, first we're going to show subgroup, then we'll show normal. So for subgroup, we have to show 3 properties: closed under multiplication, closed under inverse, and non-empty, which we show by using the identity element. For closed under multiplication, x and y are in the kernel of pi. We want to show that xy is also in the kernel. So we just follow our nose. We're going to take xy, apply pi. We could split it by the homomorphism property. Then pi of x and pi of y both go to the identity in H. Then identity times identity is identity, and that's what we were looking for. So xy is getting sent to the identity. For inverses, if x is in the kernel of pi, we want to show that x inverse is also in there. So if I apply pi to x inverse by 2 from the previous board, we could factor the inverse sign to the outside of the homomorphism. So we have pi of x inverse, but now pi of x is equal to the identity in H. The inverse of the identity element is just itself. So x inverse is sent to the identity in H, so it's in the kernel of pi. Finally, to see that our kernel is non-empty, I'll take the identity element for G, and by 1 on the previous board, we know that that goes to the identity for H. So the identity for G is in the kernel. Now, for the normal property, we'll pick some n in the kernel of pi. We're going to conjugate by x for some x in the group. Then I want to show that that's in the kernel. So if we apply pi to x and x inverse, conjugate of n by x, we break it up by the homomorphism property. Because n is in the kernel, pi of n is equal to EH. So we can collapse this, and then we'll move everything to the inside as x inverse. Now, that's equal to the identity for G, and we know that that gets sent to E sub H. So xn, x inverse is sent to E sub H. That means we have a normal subgroup. For example, of kernels, first we have pi going from G to H. We're going to send every x to the identity element. So we have the trivial homomorphism. Kernel here, everything's getting sent to the identity for H. So we have all of G itself. Okay, G is definitely a normal subgroup of G. At the other end, I'm going to send pi, taking G back into G. We're going to send each element to itself. So the only element that gets sent to the identity is the identity for G. So our kernel just has one element in it. We have the trivial subgroup, so this is going to be normal in G. For something non-trivial, take our sign representation on S3 into plus minus 1. The kernel, just going to be all elements that get sent to 1. So it's going to be the identity and the rotations. We saw this is going to be a normal subgroup for S3. So that checks also. Now, let's see what the kernel is for our quotient homomorphisms. So here, I want to consider all x and g such that q sub n of x is equal to the identity. In this case, the identity in the quotient group is just n itself. So that means x times n is equal to n. Only way that this can happen is if x is already an element of n. So that means the kernel of the quotient map for n is equal to n, and by assumption, n is normal in G. You'll note here, this is a precise statement. The way I go from n to homomorphism is by quotient map. To get back to the kernel, we just take n itself. Now, one last note, if we have two homomorphisms, so one going from G to H, one going from H to K, then their composition is also going to be a homomorphism. So the idea here is, if we start in G, we push over by the homomorphism, we're preserving the multiplicative structure. If we push over one more time, preserving the multiplicative structure, it's the same as going from G to K, preserving the multiplicative structure. Now, to see this, we'll take our x and y and g. We have our composition applied to x times y. So how do we evaluate a composition? Well, we just collapse and use parentheses. So we're first going to evaluate the term in the middle. But by the homomorphism property, this is pi1x, pi1y. For this product, we could split it up using the homomorphism property for pi2. So I'll have pi2, pi1x, pi2, pi1y. Then we note this is just pi2 composed of pi1 evaluated x, and likewise for y. So we have our homomorphism property.